So I was in Heidelberg for some time, and then I came back, and then did not want to lose it. Yeah. So what is that I wanted to do today is not on my research at all. Okay, you bear with me. I know 2026 is the 100 years of Schrodinger equation. I wrote in the title. Sanjay is 60, but Schrodinger equation is 100. Okay, and I wrote it here. And I did not write it. It's Schrodinger who wrote it, who was in Alps. Okay, enjoying vacation. Yeah, he wrote it. There is no proof. There is no proof. This was a postulate in quantum mechanics. First of all, I told you this. There is a proof. Anyway, I did also work out from wave mechanics, but there is no proof of this equation, and this equation is called an initial value equation. Why? Why? I tell my students, you cannot solve it unless you know phi of t equal to 0. You do not know it. This is not an eigenvalue problem, initial value problem. Here he is. He survived from 87 to 61. Yeah. Somebody called me and told me that no, this is Sushanta or Schrodinger. No. I wrote the year. Okay. So Schrodinger was there. He was born in 1887, Vienna. Mother was from England. Yeah. Elementary education was at home. Yeah. Yeah. Mostly inspired by his father. At the age of 11, he moved to a gymnasium. Yeah. Mostly studied languages and he didn't like it. Yeah. Married Anne. Okay. He had many academic positions with Max Wien, yeah, Einstein, and so on. Yeah. You can see in this slide that. Now, the dawn of wave mechanics was created by Schrodinger, okay, in 1925. Late 1925, in the late 1925, he was in Austria, he was in Alps, and he drafted the equation. And the equation was published in early 1926. One of the greatest achievement that we cherish today. Quantum mechanics is 125 years old, but Schrodinger equation is 100 years old. Okay, but still that equation has gone so many places. I don't know. In science, in chemistry, in theoretical chemistry, I know where it is because I have been doing with Schrodinger equation so far, but it went out. It went to industry and everywhere now. Huh? So he published General Theory of Relativity with Einstein, 1916. I'll tell you where the Einstein connection comes. Awarded Nobel Prize in Physics. Yeah. And 1944, inspiring book. A book is there in my basket. Okay. What is life? Very nice book. He wrote. Returned to Vienna and breathed last. As I said, I don't want to exaggerate on this. Now, history gave the way. How? 18th and 19th century physics failed. Okay, what was the reason? Yeah, so I can get back to 18th and 19th century physics, but I will not. I'll give you some enumeration here. Yeah, this is the classical mechanics that I have. Yeah, I have Newton, I have Hamilton, I have Lagrange. Okay, so they are all there in classical mechanics, and we used to do classical mechanics because of them. Okay, and each equation had problems. So I learned something. The second order differential equations are lot more yeah, lot more problematic than first order. So Hamilton came forward, and I solved Hamilton's equation. Today at this context, I will remember Sanjay Kumar. When I joined Sati's lab, so he was the person who was 2 years senior to me, and he taught me how to do classical mechanics. I did not do it for my lifetime, but I did it. I now do it because of some reason, and that will be reflected later. But this Hamilton's equation of motion was taught to me by Sanjay Kumar. Okay, great. So this is what it is here. I cannot determine the position and momentum simultaneously for a quantum system. Why? There is an uncertainty principle. Yeah. So phase space does not exist. Okay. So I do not have a phase space. So now this is taken from Wikipedia. You will see that no, I'm talking about classical mechanics here, quantum mechanics here, relativistic quantum mechanics, and quantum field theory. And then I have an arrow here. Mass and speed, they matter. Okay. Okay. Size did not matter here, but the speed matters here. Yeah. You are on a bicycle, but you are going with a light. Consider the speed. Yeah. So relativity only comes when you have relativistic mechanics or quantum theory, right? Yeah. This is the relativity. The momentum can be expressed in terms of the velocity and the velocity of light. See, here m is the particle mass and v is the velocity, right? T equal to mv. Now, there were some development. Lagrange's differential equation was not taken up, and today we don't do it. We take Hamilton's equation. That's okay. But did we get the answer to the question arose in 20th century? I would say, if I can say, no. Why? A series of experimental observations failed interpretation of classical physics. First one, that all of you know, I don't have to tell you. This is black body radiation, which failed, and then we came across this equation, which was a very bold postulate of Max Planck, E equal to Nhν, that gave birth of quantum mechanics. You talk about harmonic oscillator also, yeah. The energy equation, black body radiation, everything is quantized. Okay, quantized. You go on steps, right? Steps one by one. Yeah. In between you have nothing. Nothing. Classical mechanics do not give you. The classical mechanics is a Newtonian mechanics, but lot of physics there. Stokes shift. Yeah. You can see there. Absorption and emission. Now I came to this photoelectric effect. What is the difference that I wanted to point out here is the photoelectric effect is not due to Einstein. The observation was done by I wrote it. Heinrich Hertz. He was from Germany. He was an experimentalist. Einstein only gave the interpretation to it. Yeah, and he took a different path from Max Planck. Yeah, that of late I knew that no, he took a different path, that when the black body radiates, Planck considered is at wave, but Einstein considered it as a particle, because a particle hit a particle and it's a collision problem, and then he had a different interpretation of Max Planck's quantization. Okay, but photon did not come from Einstein. Okay, photon came from Jean Louis. Okay, genius, huh? Made a suicide. Wave particle duality. Okay, I don't consider it very seriously, but anyway, so a mass. Wave particle duality is, it is mass and velocity. They have the relation. Yeah, I have this here, h by mv. Yeah, and v is the velocity and m is the mass. And then you can see when you are in a train. Let's say you are moving in a train. The train is in a high speed. You feel some wave character, right? Yeah, you feel some wave character there also. So mass and velocity, they compete each other for wave particle duality, and I do not want to expose on this. Yeah. Now, this is an important discovery. Okay, after Rutherford did for the classical mechanics and then Bohr. And you tell me today I don't buy it. That Bohr did quantum mechanics. Bohr did not do quantum mechanics. Bohr took the concept of Max Planck, did a quantization of the angular momentum and put it in Rutherford's theory and got the atomic spectrum. Yeah, that was very nice in those days. I don't think, no, I did not write the year when Bohr did it. Xn is quantized, right? General, this is a general quantum condition that PdQ, PdL or whatever it is will be equal to Na. This is Bohr quantization, MVR equal to NH by 2 pi, and Planck's quantization is En equal to NHP. Now, I come to this because I have to come to this. I like this guy. Delta x, delta px cannot be determined in quantum mechanics. Yeah, I tell my students that no, you can't do it. And this guy, it was a thought experiment, and in German it is called Gedanken experiment. Gedanken, thought experiment. And he decided this is this. Although there is a proof for delta x, delta p greater than equal to h by 4 pi, I can do it with operator algebra. But delta E delta T, I cannot do it so easily. I have some proof with me. I did it for my student. Okay. So delta E delta T, it opens up a gateway for spectroscopy. Okay, molecular spectroscopy, line broadening and other things that you get everywhere. Yeah. So this is the one that gives you natural broadening of a spectrum, electronic spectroscopy. Now, Bohr's correspondence principle. Why do I fail upon it? Now, I know the classical mechanics and quantum mechanics can converge with each other. Okay, at some point. I will not tell you about now. I cannot tell you about Poisson bracket and quantum mechanical commutator. Yeah, they also have a relation. So what I show here, that if you take a harmonic oscillator wave function and go to very high level, you see this scenario what I plotted here. Huh? So the two turning points will have high amplitude and then you do not have anything there. So in a sense, if you go higher up, so you will have a continuum of states. Okay. So classical mechanics and quantum mechanics, they converge each other, and that is called Bohr's correspondence principle. Okay. It was given in 1923. Now, it is the non-relativistic Schrodinger equation. You know, this is the time-dependent Schrodinger equation I wrote, and then this is not an initial value problem. This is an eigenvalue problem. This is an initial value problem. So you have to express the wave function, and you express the wave function in Hilbert space, where you have the known functions and unknown coefficients. That's what I did here. Okay. And now, this is a guy who gave us something, some prescription. I wanted to, I know, I have lot of respect for him, Max Born. You go around Germany and then you will see Max Born Institutes. Okay. Max Born, 1926, he postulated this, that wave function is not visible because it's a complex quantity, but square of it can be interpreted as a probability density. That is what he did. Okay. So this was, and then I come to spin a little bit. I have time. So I can talk about spin and antisymmetry principle. Yeah, spin was detected late back in 1922 by Stern and Gerle. Okay, they did an experiment on argon or with silver atom, which has a 6s electron, but they got two spots on the screen and they did not understand why. S electron cannot have orbital angular momentum. Yeah, so it should go straight here. But S electron gave two spots. That was the discovery by Stern and Gerle, and then came, before him, I don't like him. Okay, before him, I'll take you to Uhlenbeck and Goldsmith, who were doing PhD with Pauli. I'll show you. So Pauli's photograph next. Okay, so they did interpret that why it can happen. Okay, and then today we know spin is because of Pauli. No. This is spin. Okay, and spin is a vital quantity that we always now we know that spin is a vital quantity. Yeah. The Pauli was, anyway, I will not say anything. Okay. Let me have my respect to Pauli. I will not say anything. Now, this is what it is. When you get spin in the wave function, then you do not have the wave function in its form as Schrodinger proposed. You have a spin in it, so you have to put the spin. When you put the spin, wave function not really remain one dimensional wave function with only spatial coordinate, and you have a scatter determinant. Yeah, you call about spin orbital, right? Very nice. Particle in a box, you do the quantization, and if you recall, if you have a free particle, then E will be h bar square k square by 2m. Yeah, t sine kx d cosine kx, and you don't care about it. This is a free particle which can move everywhere. Yeah, and then when you confine the particle in a box, no, I think I should go back. Yeah, when you confine the particle with a condition which is called boundary condition, okay, which is called boundary condition in quantum mechanics, and that you need to have things quantized. So it is here. It is in the last equation. You have the particle in a box equation where the boundary condition was there. You have harmonic oscillator. Yeah, you will have the same thing, same scenario. You have nodes, wave functions, everything. Hydrogen atom. Yeah, this I talked about, and now what I did not talk about, now I will come to that because I have another 5 minutes. Huh? Yeah. So what I did not talk about, in Schrodinger formalism, I did not have any spin. Spin was not there. Okay. So when I want to consider spin, because spin exists, that all of us know, and spin did not get a Nobel Prize, so to say. Okay. The thing is that spin did not get Nobel Prize, but we need spin. Then equations are derived. One is by Klein-Gordon, what is on the screen that you can see. Huh? And then next will be more specifically Dirac. What we do in Schrodinger mechanics is that we take the spatial wave function, then I attach some spin to it to make the wave function anti-symmetric. That was Pauli. I don't have much regard to Pauli. Okay. Anyway, you can take it otherwise, but I don't have. Yeah. So Pauli principle, we thought, no, we have to make the total wave function anti-symmetric. That is what we do. And now the next equation is here. This is my last slide, and these two gentlemen, I think I have lot of regard for both of them. Yeah, this is Erwin Schrödinger and this is Paul Dirac. They got Nobel Prize in 1933 in physics. Good, very nice, very nice. I thank you all for listening to me, at least. Yeah.